Okay, good afternoon everyone and welcome along to this Energy Futures Lab lunchtime webinar on low carbon transport. My name is Conor McNally, I'm the Communications Manager at Energy Futures Lab. I have the pleasure of welcoming this week's speaker, Professor Ricardo Martinez-Botas. Ricardo is Professor of Turbo Machinery in the Department of Mechanical Engineering here at Imperial, and he's the Energy Futures Lab team lead for low carbon cities and transport. He heads up a research group in the area of low carbon vehicles, with a particular emphasis on highly downsized engines, turbochargers, and energy storage and recovery systems. And he has developed the area of unsteady flow aerodynamics of small turbines. Ricardo is also a member of the Science Advisory Council of the UK Department for Transport. And in 2016, he was the independent expert who oversaw the vehicles emission testing program set up in the wake of the Volkswagen emissions scandal. A word about how the webinar will work. Ricardo is going to speak for around 30 minutes and then he will take your questions. To submit a question, use the Q&A box on the right hand side of your screen. And as always, please put your name and affiliation with the question, as you would do if we were in a room together. So with that, I'd like to say a very warm welcome and hand over to Professor Ricardo Martinez-Botas.
Okay, thank you, Conor, for the introduction. This is a pleasure to give this seminar and this webinar at the EFL lunchtime series. So I like to just focus on the title. The title is around low carbon. It's around CO2. The intention of this seminar is to outline the main contributors to what drives CO2 in vehicle technology. That's really what I want to bring in this seminar. Is there not a lot of technical elements? It's mostly bringing together what I think drives CO2 in a road vehicle particularly. And we're going to look towards 2050 to some extent with the help of some of my colleagues. So if I has acknowledged the Turbo Group at the Department of Mechanical Engineering, part of the Thermofluids Division. This is where my research group sits. I'd like to acknowledge a good friend at Oxford, David Howie, Greg Offer, and Dr. Sritha Raju at the University of Technology Malaysia, where we have a joint center. So what drives CO2? First question, what are the mid-term technologies? Why is energy carriers, why are they so key? I think we're mostly familiar with most of these aspects, but I'd like to bring them together in one single equation that would help all of us visualize the relative importance of these elements. I'm going to talk about energy recovery briefly in 2 slides, and we're going to look at some bad news and some good news, which hopefully will never be bad and mostly will be good as time progresses. If you look at the vehicle has many elements. So this is a picture of a road vehicle, mid-size, maybe. You have many elements. You could work on infrastructure here on the top right. You could work in analysis of techno-economics. You could do transmission energy. You could do conversion. You could do IC engine research. You could do electrification research. You could do storage research. You can work on machines, electrical machines, control, and system simulation. So it's a whole plethora of things one can do. And of course, one does do if we want to move transport towards the future. The point of these slides is not to focus on any particular item, it's just to show you the very large number of items and the complexity of the image. So which is the most important thing to work on? What should I devote most of my energy, time, research funding, industrial research to do if I want to tackle CO2? To help that, with Dave Howie, we had a look at an equation going back several years, many years, and this equation is going to be put here. This is the only equation I have. It's rather simple, but it's one that is worth understanding. If we're looking at CO2 on the left-hand side, we say CO2 is equal to 3 things multiplied together. So that's as complex as it goes. You got something called D multiplying something called E, something called F, the last term. They're all multiplied. So the first thing to note is that if I minimize any of them, and I'll tell you in a minute what they are, if I minimize any of these components, D, E, or F, I make CO2 smaller. And they compound each other. A bit of a change of D, a bit of a change of E, a bit of a change of F, compoundedly will give you, of course, a larger change of CO2. Second thing you note is that if any of these terms is 0, the total CO2 would also be 0. All fairly evident and simple mathematics. So let's see what the first term is. The first term is called demand, D. And I'm going to say this is vehicle kilometers. This is global net countryside, I don't particularly mind the vehicle kilometers traveled. No wonder we call it D, because that's the demand for traveling. The next term is called E, which is the energy conversion. It's how much energy do I need to move 1 kilometer? I have to travel those kilometers. I want to know how much energy will be consumed to deliver a single kilometer of movement. And where CO2 is contained is on F. F is the CO2 per unit of energy. So how much CO2 is contained in 1 unit of energy in order to deliver 1 kilometer of travel, in order to deliver the total vehicle kilometers travel, and that will give me the total CO2, of course. So it's 3 simple things. You know, if we can minimize we'll get a gain, and similarly E and F. So all of them are equally important, one could say, if you look at the simplicity of this equation. They're all equally important. The question is which one is the most likely or easier handle or lever I might have in order to reduce the total CO2. So stay with me, vehicle kilometers times energy per kilometer times CO2 per unit of energy. I'm going to take each of them in turn and try to explore with you actions that could one take, individuals as well as developers and researchers. The first one is vehicle kilometers. Well, what drives vehicle kilometers? Well, many things drive it. The mode of transport, of course. We're going to see a picture in a minute about modes of transport. The cleaner the mode and so on. We could talk about that. But the one I want to talk about here is road vehicle or transport of several people or just one person. The first one is the vehicle kilometers. So that is primarily a function of 2 things: the demand and the occupancy. So remember, the first one is passengers kilometers, that's the demand. A single person like me might want to travel to Imperial College from Twickenham, and that would be me traveling so many kilometers. But if I go on the way to Imperial College, I choose to share my car or choose to find a different mode of transport which is not individual, that will determine the passengers in that vehicle. You can see directly the first lever is that if you can increase occupancy, you double it, because it's in the denominator, it's demand divided by occupancy. You double occupancy, you halved D, and because it's compounded, you have CO2. First lever, traveling with others in the same vehicle, all other things being constant, will lead to a substantial decrease of CO2. That is an action that we as individuals can take. So occupancy drives CO2. Of course, the demand too, if we want to go to an economy which is less movement, an economy that is more isolated than we are now, an economy that there is some boundaries and geofencing, you would say that demand can also be reduced. But somewhat development and movement, or rather development and desire for movement, goods and people, do go hand in hand. We might prove otherwise in the future, of course. So the demand. Occupancy, I don't want to see anybody traveling alone in a car, because that is immediately the highest D you can get. So if we look at a modal shift I mentioned, I'm going to have a slide in a minute, which is here. So we could shift to different modes of transport. Now moving into E, how much energy to travel needed to travel a single kilometer. And I've got some images here. These are by no means giving some ranges and by no means backed up by a deep level of science, just a look, a bit of common sense on our modes of transport. The first one, if you walk, and here's a nice walk, and you walk a unit of energy to move a certain distance, no matter what hour per kilometer is the appropriate one here for energy, is 36. The number 36 is not hugely relevant because you don't know what to compare it with. But if I compare it to cycling, you might say, well, that's about 16, because cycling is a rotary motion, it's a cyclic motion that requires less energy to move a certain distance. While walking is not a rotary motion, it includes your muscles moving in usually linear direction, and therefore you consume more energy. But so now you're starting to get some comparisons. Interestingly, if you go to the underground, I could put a range here. You could say around 90 watt-hours per kilometer. So yes, it is more energy consuming. Many reasons for that: friction in the vehicle, underground, lights, there's a whole host of reasons, aerodynamics, and so on, that would affect that particular number. But it's certainly far more energy consuming than cycling and walking. If you take a bus, and this is not the best picture for a bus stop because there's lots of people, not all buses have this large magnitude of people on the bus stop. But I put a range, and the range is needed because, of course, some vehicles, some buses are regen braking, some buses are hybrids, some buses are fuel cell buses. It's a whole range of buses, but for a typical bus journey, somewhat between that 163.20 watt-hours per kilometer. So a lot of mass we're moving from A to B, a lot of the time per passenger, I should say. Everything here is per passenger. A lot of the time, you've got a lot of mass movement and a relatively small occupancy in many of the journeys. Having said all of that, how is a car compared to this? If you take a vehicle, a normal mid-sized vehicle like that picture, that's about 600 watt-hours per kilometer. So you see, immediately you say, indeed, the energy needed to move from A to B for a standard-sized vehicle is substantially higher than anything else. That I think we mostly knew, but now we definitely do know, and I have some evidence to back up that number too. So indeed, if you now decide to go with 2 people, that goes to 300. And you go to 4 people, you go to 150. Now you're starting to get somewhat competitive to the other technologies on this picture. So it is good to put things in the right order. Part of my talk today is about classifying, simplifying, but achieving some outcomes of this talk. And this is the purpose of this particular slide. It's not to fixate on any of the numbers. It's to realize the order of magnitude. When you take a car, this is what you will incur in terms of energy usage. A bit more engineering base. I'm at the Department of Mechanical Engineering. So you would see here a little bit of mechanical engineering going on. So what drives the energy for 1 kilometer? Well, first of all, the car we had earlier. Just remember this image, about 600 watt-hours per kilometer, a lot more than the others, and just one person. But what drives that energy? Well, one thing that drives the energy is the conversion technology. You have an efficiency divided by the energy needed to move 1 kilometer, divided by an efficiency is going to give me the energy per kilometer. What drives the energy to move needed, not the energy needed to move 1 kilometer? Well, drives really 2 significant elements. A bit of mechanics. We all know that your speed of motion is significant when it comes to loss, aerodynamic loss. We also know that the speed of motion is also hugely significant when it comes to rolling resistance, but that's only by weight. So that at a given time, the energy to move from A to B is driven by 2 elements which have an addition, a plus sign. It's how much you lose in aerodynamics, which is the shape of your vehicle, amongst other things, frontal area and shape. And added to it is the resistance to move due to the wheel and road interaction. Important topic here is that the rolling resistance prime element is the weight. So shape and frontal area and weight. They are the 2 parameters, and because there is a plus, they're both important. They're both, I wouldn't say equally important, depending on the forward speed. As you know, the aerodynamics goes with the square of your forward velocity. Very straightforward analysis. But you see, that's a given time. What I want to perhaps get to now is this lower set of words. At any one time, as a driver, you may be doing a whole variety of actions. One is to go in steady state in a motorway at constant speed, 60 miles an hour. You might choose just to follow that, and there is no change. There may be an inclination change where you go slightly inclined of that road, fine. But generally, you might just hold that speed constant. But for the rest of your time, you're likely to be doing several things. You're likely to be accelerating. You're likely to be coasting. That is an important element I did want to emphasize. So one is don't travel alone. The second element I want to emphasize is the mode of your movement highly determines the way you behave in your vehicle, highly determines your CO2 footprint. So if you think of a high-speed train as an analogy, a train that goes from A to B at high speed, then you might see how the train starts coasting towards the station several miles or kilometers ahead of destination, using the natural resistance, using the natural braking energy of air and traction to get to destination and avoid the use of a substantial use of the brakes. And they might use the brakes and regen brake it. Well, when one drives, what is in our mind as you approach an obstacle? You might say the obstacle being traffic lights. It may well be traffic on the motorway and you have to slow down. What is our thinking process? Our thinking process should be one of coasting. I can say, all right, instead of braking at the last minute, wasting lots of thermal energy generally, even with regen braking, I'm going to allow that coasting behavior between as I approach the destination. Not always possible. You may be in traffic. You may not want to slow down the person behind you. But as a driver, you've got an enormous lever here. I'm hoping that all vehicles, either when you brake, they recuperate. There should be no vehicle sold where braking and recuperating do not come hand in hand, because you want to take the kinetic energy, Newton's second law, the kinetic energy of the machine, which is enormous, 1.2 tons, 1,200 kilos. This is what you're carrying when you're moving in that vehicle, or so, a little less, maybe in some cases, a little more in others. You want to recoup some of that braking, some of that kinetic energy. Now, the important item here, I've put efficiency. So interestingly, as you think of vehicles will become heavy due to being electric vehicles, you may have a Tesla being a heavy vehicle insofar as that it has a very large battery system, many hundreds of kilos. And of course, you're now increasing your weight, and increasing your rolling resistance follows through that argument. And but the conversion efficiency is high. So yes, indeed, your vehicle overall is more CO2, lower CO2. But do remember that the more batteries you put in, the heavier it becomes, the more rolling resistance. Even though we have a high efficiency, there will be a crossing over point in which there is no point to put any more batteries. I'm thinking also of heavy duty trucks. The attempt to electrify those is not being discussed, but you understand now why it wouldn't be. Because you are directly increasing your weight, and eventually for a long journey of hundreds of kilometers, it does not make sense. You cannot break Newton's second law. If you increase your weight, you're going to have to deal with the rolling resistance associated with it. If you got a combustion engine, which we're going to see in a minute, indeed, a combustion engine, the weight may all be lower, the frame of the vehicle may be lower. There may be reasons why the overall weight can be substantially lower, but of course your efficiency conversion is poor, very poor, and therefore the net is that even though you're lighter, your efficiency conversion drives E up, and therefore that will be a less efficient system, or less energy, a more demanding energy system. Let's look at a bad picture. This is a bad picture. This is what an internal combustion engine does. A combustion engine will take some energy from the fuel tank and convert some of it to useful power, useful movement. I mean, let's say 10 to 15 of useful movement with drivetrain and accessories, maybe 15 to 25%. So let's call it a quarter of the total fuel content. I've only been able to use a quarter of the total fuel content. The rest, 60% worth of it, is in the tailpipe through heat loss. And some of it goes to all the losses, which are here labeled as idle, deceleration, pumping loss. So yes, indeed, an internal combustion engine as a machine, while it powers 99.9% of most of the road vehicles today, the great majority by a long way, it is losing a substantial amount of heat energy to the environment. So in my group, this is an image of well, as far as a Formula One engine, manifold, and has a slightly exaggerated, but not far off. Some of these are glowing red just by the nature of the high temperature in the exhaust. And the point is that we work in my group on making the engines more efficient as well, and that, as we'll see in a picture, has been tremendously important in making sure E the middle term of my equation is low. So we work on all these systems, improve combustion through reduction in order to reduce emissions, exhaust energy recovery. We've got several concepts that will aim to waste heat recover some of that 60%, hugely important, and the use of other advanced systems like thermoelectric generators to get some exhaust system recovery into electrical storage or some other mechanism of storage. What I think the trend is towards 2025, which is ever closer. It is a more electrification to 2025. You'll see, of course, huge developments on battery-driven vehicles and hybrids. But I think you'll also see a lot of developments on current technology, which is being more electrified. Your engine becomes a smaller portion of a more electric machine. You might have electric turbochargers, electric waste heat energy recovery systems, and electric boosters. So I think there will be substantial effort still towards electrification of the current system. Now, that's not going to take us as far as we want to go. We'll see later. If I show you one technology that we've been involved in, is the idea of making engines smaller. So that's a 3 liter and that's a 1.4 liter behaving in a similar way, and yet achieving a fuel economy of that kind of magnitude. So this engine here at the bottom is somewhere between 25 and 35, big range, because we got involved into 2 programs at Imperial, and somewhere one of the programs was closer to 25, the other one was closer to 35. One is a 1.1 liter engine, gasoline engine, the other one was a 2 liter engine. So substantial gain. So yes, our engine technology has enabled E to be reduced by that kind of magnitude. And as we already alluded to, is not sufficient. And then we move into hybridization. We'll talk about that in a minute. That happened to be the program that I mentioned earlier. So more electrification, more complexity, more electrical machines and conversions into the drivetrain. Unfortunately, higher cost too, because of course, the more complex technology, the higher the cost. And demonstrated on the road, high boost, led by Ricardo, which is not me, a consultancy in the south of England, and others, including Ford. 38% fuel economy. The vehicle began as 16869 grams of CO2 per kilometer, ended up with around 102.9 grams per kilometer. It's worth noting this. Of course, that takes us as far as a few years. I'm going to pass this because there's little time, so I'm just going to go straight into my final term, F. So we said D drives demand, E drives how much energy is needed to move 1 kilometer. What about F? Well, F contains our classic fuels. And our classic fuels have a big cross over it, meaning no please. And perhaps more advanced fuels, advanced biofuels, synthetically derived fuels, hopefully sustainably, and synthetically derived fuels, and electricity, hopefully, an electricity with low or zero carbon content. If we can achieve this distribution of NIA's net zero carbon content, then indeed, which can never be done can never be done. It's not feasible to do it with conventional fuels. We can get F to near zero, which is the objective of the government, 2030, 2040 target. So we need biofuels, synthetically fuels, and electricity, all sustainably derived. That will make F near zero. Of course, if F is near zero, no wonder we focus on fuels and energy carriers, because if F is near zero, then indeed CO2 will be near zero, no matter what D and E is. And hence, indeed, the only term that can make zero is F. Hi, I think I lost that. Hello? Okay.
Yes, you're back with us now, Ricardo.
We're still back on? Okay, okay, so I'm back on. Apologies, that seems to be the internet is playing up here. So if the only thing I can make really zero is F. Because you see, you can't develop a machine that has no energy need to movement. Well, I can't think of one. And we're not going to become a isolated, 100% isolated economy without movement. So indeed, F is the source. Now, I don't have hydrogen here. It's not because I don't like hydrogen. I put it within synthetic fuels. Let me show you briefly what I think the world might look like as we move towards 2050. What will be the composition of fuels? And I've chosen the ones given here, equally weighted at the moment. Electricity, hydrogen, natural gas, liquid biofuel, I mean sustainably derived bio-liquid fuels. That is sustainably derived through a process of either capturing CO2 and getting a break of the water molecule to get hydrogen and then putting it together into a sustainable liquid fuel. That's what I'm talking about, liquid biofuels. And then the standard liquid solid fuel, which may be needed in some applications. But I don't know what the world will look like. This is a possibility where I think the world will be heavily dominated by electricity for movement. I think you will have some areas so high hydrogen content, areas where you might not be able to deliver your electrical motion simply because of the power density needed in terms of the weight and batteries to be carried. I think there will be, hopefully, in my view, a large demand for this sustainably net zero liquid biofuel. There'll be some natural gas, and there will be some required liquid fossil fuel of today's idea. That's kind of a hand-waving statement that I think is my current hand-waving statement. I'll pass that. So we look at energy recovery. I mean, one of the items as I move towards the second half of my presentation, I've done most of it. I've got about 5 minutes to go. I work in our team, we work on energy recovery. I said in my abstract that energy recovery was important. And the point here is that you are using energy in a combustion engine and any thermodynamic machine, typically in a ratio 1/3, 1/3, 1/3. It's given here 1/3 in the tailpipe, 1/3 in the cooling of the system, because otherwise you will melt down, and 1/3 would be the output. So 1/3 of energy recovery, energy usage, and then 2/3 of wastage, at best. I mean, I showed you a picture earlier, which was worse than that, but typically in a good operating mode, you should be able to get 1/3 of energy conversion. So it's absolutely crucial we make better use of this energy content. So in the exhaust, you might have flow energy. You want to convert to mechanical energy. You might want to convert thermal energy into electrical energy, or you might want to convert thermal energy into thermal energy. So there's three things here. I mean, we've not seen this before. I'll take just a minute at most to explain. You could say, I'm going to put a mechanical turbine in the exhaust to take energy from the exhaust and produce electricity through a generator on that turbine, or something similar. I will call that flow energy to mechanical energy. That exists today. And we can tackle the 1/3 of the top equation. The 1/3, at least I can tackle it this way, if not the 2/3, but at a minimum 1/3. Today's more advanced ideas are talking about getting thermal energy direct into electrical. So that means through a secondary cycle, what we call an organic Rankine cycle. You take some of this thermal energy, put it through a effectively steam cycle, not quite steam, but a refrigerant cycle, really, and then you take that energy out into electrical form and store it. You can do even better than that if our technology, our scientists, our material scientists, particularly here, as well as others, can transform thermal into electrical. Wouldn't that be wonderful if we could do that? Well, we can do it through an effect, Seebeck effect, which is what drives thermoelectric generators. You get thermal energy straight into electrical energy, straight into storage. Wouldn't that be wonderful? And if we can make that efficient and cost effective, that is an area of excitement if I was a new researcher entering the field, which I'm not. Finally, even more exciting, we could take the thermal energy of any process, including an IC engine, and store it. And we can store it for later use. How often do we use energy for a purpose direct? Sure, often. How often we use energy and then we waste a lot of it, and then later on we want the energy back, or you want a cooling effect, or you want to get air con. So that is what I call thermal energy into thermal energy. And of course, the current status is that today it is available to do flow energy into mechanical energy. Today is less available to do thermal energy into electrical energy. So the area of research is higher. And in the bottom of this pyramid, the area of research is even less known. So no wonder we talk about thermal storage as a key element that is fundamental when it comes to any thermodynamic machine. So the future opportunities are much higher, of course, in the years to come, if one can come up with the science, the materials, the storage mechanism by which you can store thermal energy into thermal energy for later use. Thermal energy into thermal energy for later use. That is a good topic if I was writing a new proposal as a young investigator. I think thermoelectric generators will be fundamental. I think in the futures to come, there's lots of things still to be done on those because the efficiency is low, but it would be a future opportunity at the top of the pyramid, and then lesser and lesser, because at the top of the pyramid, which is inverted here to demonstrate this, is actually already available today. The reason why we don't do some of the things at the top of at the bottom of the pyramid here in purple is because they are not cost effective, and therefore there's a whole mechanism of making it cost effective. Let's look at some good news and then some bad news. And this is not my chart, but it's a chart I think is rather good, which is a chart against time, going up to 2049, 2050 effectively. The vertical axis is the vehicles on the road. It's an important chart. 1,000 million, so 1 billion. 2,000 million, 2 billion. Global. This is the vehicles on the road globally. And here we're looking at technologies in whatever order. I more or less put them in a certain order. Don't have to be like this. Fuel cell technology, battery technology, plug-in hybrids and hybrids. And this is what we call low emission vehicles, ultra low emission vehicles, or zero emission vehicles on the tailpipe. And here I've got a little element which I've not moved from when this chart was made some years ago. And we wanted to get, or rather, with the help of Greg, we wanted to get 20 million of these vehicles by 2020. Now, 2020 is, yes, today, yeah. That was a prediction at the time. Well, we're actually not even today at 20 million. That's a disappointment, isn't it? That's something that, you know, the market hasn't been able to penetrate these vehicles for many reasons, and we are somewhere in the sort of the 10 plus millions of these vehicles today. So as I project and say, right, what's that going to look like as we get to 2050? Well, it will hopefully, by the way, to 2050, we get lots of technology which is cost effective. It drives this innovation chart to some sort of curve. This curve drives me to some sort of upper point at 2049, 2050, and that looks like about 1.25 billion vehicles, 1,250 million vehicles. Globally, worldwide, in all modes, right? But not air, road. And that one would say that's really rather good. That's excellent. So the good news is I believe in this innovation is going to kickstart soon. We are past somewhere driving towards 2030. We'll get a few 100 million, and then we'll soon get into hundreds of millions, and then we'll be decarbonizing, of course, through the efficiency as well as the generation of the fuel F. Our road transport system. Unfortunately, there's some bad news. The bad news are well known. Today, about 1 billion vehicles in the world, or somewhere around 1 billion. So we can go up here around 1 billion, of which about 13, 14 million vehicles are these low emission vehicles only. And as we predict a normal medium case scenario growth of wealth globally in the nations that are developing fast, as well as the current developed nations, or the economies that we know, we will see a growth. And so in this growth, you could have a medium scenario that one can say that unless something else changes, there will be 2.5 billion vehicles by 2050, 2,500 million vehicles. And so if that was the case, this growth rate here is not near enough sufficient. One consequence. Second consequence, the number of vehicles in 2050 is approximately similar to the number of vehicles today, which are based on combustion systems. Now that legislation might tell us otherwise. We might locally legislate and provoke a different change. That is what is being proposed. But ignoring all of that, the scenarios are that 1, we need to innovate faster. 2, unless we do something about it, we will end up in a position I don't want to be. And the third most important thing is this top curve can be curtailed by demand, car sharing, and shift of modal transport, as I said at the start. This demand here does not have to follow that curve. It would go up. If you see my mouse, it will then level off, and it might even reduce as we get closer to so higher up in time, in years. So 1, not enough. 2, it doesn't look great in 2050 unless something else changes. 3, the demand curve would have to be curtailed to enable this not to happen. So with that, I finish with this slide. It's the final slide, and I'll take questions or comments. It's a slide again produced by a Grantham Institute paper that David Howie and myself produced, and so it dates back to some time. Well, the data is still valid because in 2010 we had 160 grams of CO2 per kilometer, 2015 130 or 35, we've legislated to 95, and so it's going down. And then I've got really at the time we said 80% of the levels, 1990 levels. Today we're saying 0% by the time we get to 2040. Excuse my telephone. So we can then say whether we join at 0 or we join at slightly more than 0, we got to go a substantial way. I'm just got a straight line. What I put here is 2 bars. Is the diesel ICE minimum. We are there. We are not able to demand, even if we wanted, anything of the diesel ICE engine to get below that kind of level of 80, 85 grams of CO2 per kilometer. Even if you go to a hybrid vehicle, the minimum is somewhere in the 60, 65 grams per CO2 grams of CO2 per kilometer travel. So yes, okay, that bar is definitely lower than the orange bar, but it's still a long way of getting to 0. Compounded with that, if we're gonna then become more electrified by hybridization, plug-in hybrids and pure electric, this blue line is to continue, which is the CO2 content of electricity generation in the UK, would have to continue to go down and down. And with tremendous changes have occurred in that in the UK. Remember, it's the whole world we're also concerned about. That was my last picture. And with that, I think I'd rather take questions now. Hopefully I left you a picture that says we've got to do better, but we are doing rather well in some areas. And hopefully gave you a few tips, vehicle occupancy, driving behavior, and of course, ever increasing need of continuing to work on energy vectors, particularly on net zero energy vectors. With that, I'm happy to take comments or questions.
Excellent. Thank you so much, Ricardo, for that excellent presentation. And just a reminder to the audience that you can submit questions through the Q&A text box, which you'll find on the right-hand side of your screen. And we've already got some questions coming in there, so I'll hand back over now to Ricardo for those.
Okay. Do you think methanol will play an important role as a synthetic fuel, given it's one of the easiest to make and can be used both in IC and fuel cell, is being considered by government? Well, methanol is my prime sustainable liquid fuel. You remember in my sustainable liquid fuel there was a big portion of liquid biofuel. That is my prime one. So this is the process which is cost ineffective at the moment, and there's some energy conversion issues associated with generation today, where you take a CO2 molecule or something, a proportion of a CO2, so many CO2 molecules, you put them into hydrogen molecule, you put them together, you effectively get methanol. And that is sustainably derived, because if the CO2 was carbon captured, and the hydrogen was generated in a sustainable fashion, that would give you a wonderful fuel of net zero carbon. So absolutely see your point, and I see another point. This fuel is liquid, approximately with some level of pressure. So today could be put to the pump system of our petrol stations. That has a huge advantage relative to hydrogen and even relative to electricity. So I think I answered the methanol question. Thank you so much, Tejo, for putting this forward. I've got a question regarding the use of on heavy duty. So I said, are you aware of any cutting-edge trials being conducted on heavy-duty vehicles, i.e. lorries, using low-carbon fuels, i.e. biomethane, hydrogen? And yes, I am. I think one of my main collaborators is Daimler. Daimler trucks is the largest producer of trucks in the world, and they have moved into doing work on fuel cell technology. I think fuel cell technology for heavy duty are somewhat yet to be materialized, somewhat yet to be made cost effective, weight effective, and power dense effective. But there is a lot of excitement, because if you can get your molecules and put them through a fuel cell, hydrogen based or otherwise, then you are we have one mechanism to get to low carbon long haul transport. Yes, there are programs on that topic. Thank you, Anonymous, for your question. Sonny asked a question: what are the technical barriers that have prevented widespread adoption of hydrogen fuel cell vehicles, and how would you overcome this? Well, technical barriers, I worked on marine hydrogen SOFCs in the 90s, and the problem at the time is there was a big hype of hydrogen, big hype of fuel cells when the technology was not ready. So that's one thing. When you implement and try to introduce technology that is not ready, you're going to get some pullback against it. I think the technology is somewhat much closer to being ready, if not ready. It is driven by a number of elements, and others in Imperial are better placed than me to answer. One, fuel generation, and the net zero element of that, or close to net zero. Two, the power density of these machines, just the sheer volume per power in terms of how big it is, or weight per power in terms of how much it weighs relative to the output, yet remains a challenge. So some of these fuel cells do require onboard processing, some don't. So that's another element that did have some difficulties in the 90s when I worked in the space. So I think it is nevertheless exciting for duty, and some other applications would be a lesser penetration for standard road vehicles, so long as the electrification objective is met, in which case we do it through an electrified, hybridized or electrified. You could say a little fuel cell running on a hybrid vehicle too, which is pluggable. So I can see that too. Thank you, Sonny. We got Drew Pierce. Do the watt hours per kilometer figures for different modes include the embodied energy of the production of the vehicles? No, they don't. I'm sorry, Drew, to tell you that. They don't. They just use. E was about use. In none of my discussion, I had CO2 related production of the machine. It was use, I'm afraid. Yeah, no, they're just comparative in terms of uses. Thank you for your question, and I see your comment, and I understand your comment too. And the whole area of understanding the complete picture of CO2 is something that a large number of people work on, and I've looked into, not enough time for the talk today, and certainly presented in the past. Well, a question by Chris: how best to adapt historic vehicles such as classic cars to low carbon future? Simply ensure they are well maintained and in a good state of tune. Question. adjust to run E10 retrofit. Well, yeah. So first of all, good maintenance, sure. Way we drive them, even more important perhaps in some of these vehicles. Can they meet the emission standards? Well, that's the question. If we retrofit them and put a device that does something to them, and then the emission standards are not met, maybe met for certification, which I know a bit about, but they may not be met in reality on the road, then that would be a concern to me. Nick, thanks for the seminar. Thank you. Your final slide showed the minimum CO2 emissions for hybrid remains quite high. How useful are hybrid EVs? How useful are hybrid EVs then in decarbonizing personal transport? Hybrid EVs. Well, so again, if your generation of electricity is low and your carbon content of electricity generation is low, generally you will be driving electric in that hybrid. If your local air quality, and keep saying that because it's important, local air quality will require it. But outside the local air quality, you might then say that having to stop to recharge, or having bigger batteries, increasing the weight, rolling resistance and the energy demand may not be a good choice. You might want to have the hybrid mode for some portion of your movement. So that minimum that I had was the pure hybrid. If you do a plug-in hybrid, that bar will descend to lower CO2, depending on the mixture of CO2 associated with electricity generation and the CO2 associated with the fuel content. Hopefully I answered that question. More question. Tejo, you asked me a question. Has there been any work done yet on the waste heat energy recovery using absorption chillers for aircon on cars? Do you think this could be performed cost efficiently? Would packaging be a problem? Yeah, I think that's a great question. This is really what is embedded into my thermal to thermal conversion. It was a way, and we are working on this, we particularly elements of the group and also my colleagues in Malaysia. We're working on how to store that energy thermally without converting it through phase change material or purely through another very good medium and well insulated system. And then you use that heat at a later date, or rather when you come into the car when it's rather hot and you use that in absorption system. Why is it difficult to do? It's very difficult to penetrate the utility road vehicle market. It is so cost effective, it is so cost demanding rather than cost effective that even a mere £10 investment, let's call it a few £100 if you prefer, but certainly a few pounds would be enough for a developer to think twice, let alone putting a trigen system or a system that would use that waste heat. If I could, I would. I have a wonderful slide, no time, where I do what is the maximum we could possibly recover by the combination of absorption, battery conditioning, turbines, or running Rankine cycles, thermoelectric generators, a whole host of possible technologies. Of course, hugely cost ineffective. Packaging is a problem for some of these. I wouldn't say for your cooling system is the biggest problem, but I think it's cost the biggest problem. But yes, packaging is always a problem for light duty vehicles. In a truck, you might afford a little bit more, but in a bus, you might afford a little bit more too. Right, Nick asked me a question. Nick Gather. What's your view on e-fuels such as hydrogen from electrolysis or MEHO or hydrocarbon made from CO2, electro H2? Is it realistic aspect enough to low carbon electricity in the UK? Okay, that was what I think I alluded to. That is the sustainable liquid fuel is this exciting fuel, so long as it can be, of course, generated with a low carbon content of electricity. Doesn't have to be in the UK. You could generate that in North Africa, to call it southern Spain if you want, my nation, and you could generate it there with the excess enormous amount of sun radiation we have available, 1 kilowatt. 1 kilo per meter square, and you could then generate your electrolysis process and then produce your hydrogen and capture in CO2 and produce your methanol effective fuel, e-fuels. I think e-fuels up to recently have been forgotten. They are not forgotten today in the government policy. So they are definitely not forgotten. They can somewhat enable, if I say this, I mean it in this manner, they can somewhat enable the electrical revolution. because by putting too much need on a battery electric vehicle, by putting too much need on developing that element and penetrating hundreds of millions of vehicles needed, we are perhaps somewhat making their life rather difficult. Material availability, cost effect, essentially. So if we can still retain a proportion of our movement through e-fuels, sustainably net zero generated, why not? Hopefully I've answered your question, Nick. Another question is, are there consequences for other oil derivatives if gasoline and diesel are not required in current quantities for transport? Not sure it's 100% what you mean. I'm sure there are other consequences for other oil derivatives if they're not needed, because they're not going to be produced in a cheaper fashion. So you're not going to get the byproducts. Sure. And that would have to be dealt with. Hopefully that's enough for you. It's outside my remit to some extent. Faiz, you asked me a question. In your presentation, you mentioned a growing dependence on biofuels for cars, but in consideration of meeting future food demands and also preserving biodiversity, do they have a place as a fuel for cars specifically? So I think I might have confused you when I put biofuels next to synthetic fuels. I did want to distinguish those two. There's some really third generation exciting biofuel development, which does not impact on land and food as much, certainly, as the first generation. I was really not talking too much about that. There are other people at Imperial CEP, particularly, are really good experts on the topic. I was talking mostly about the sustainably derived liquid biofuel, and I call it bio because it comes from the bio element, not because it comes from plants. I'm sorry, I might have confused you with that word. Tom says, excellent presentation, thank you. Hydrogen can be converted to ammonia, thank you, which could be used as a fuel since it has a high energy density. The combustion is more difficult, but do you think ammonia has a future? Well, yeah, indeed, combustion is different, but not substantially different. First thing to say, using ammonia in a combustion system is different, but not substantially different. So I think the transformation needed for the base machine is not huge. Question with ammonia is often around safety, or rather toxicity. Smell can be dealt with, but is toxicity a big issue? I think ammonia is really being considered, and I would really encourage research on that topic. Particularly excited for the use of ammonia for marine systems. Marine have very few options, ammonia being one, and as you can say, can be sustainably derived for hydrogen. What is the common in all of these questions on fuels? The common is hydrogen. So it's your hydrogen vector. We know very well. But it's ever more present in my mind. It's the hydrogen vector where we need to put all our effort. Without hydrogen, none of these fuels which are sustainably derived in this manner, as far as I can see, except the bio generated through advanced systems, are going to make it. So yes, we need to get the energy vector to hydrogen to continue. I think we got just one more question, so I might have just made the 1 hour. Question covering D, E, and F from a personal usage perspective. I remember your lecture in 2010 saying that you drove a 2-liter diesel as your car. What do you drive today, and what do you think you will drive in 10 years? Well, I'm sorry to disappoint you. I still drive the same 2-liter diesel car. So I'm afraid I have not changed. It has been upgraded because it was one of the cars that was in the Volkswagen scandal thingy. So I did have to get it retuned, but I can make you at ease saying that my mileage per year is not much more than 2,500 kilometers, or miles, sorry. So I really do not use the car very much. It's not an excuse, it's a fact. I really do not use it. I have an asset, indeed, poorly utilized asset, but it is out there. What would I drive in the future? Without doubt, I would drive a plug-in hybrid electric vehicle. For me, if I stay in London for the foreseeable future, and I had a charging point outside my home, I don't have a garage, then I think I might well consider pure electric. Right now, I cannot possibly consider a pure electric car. It's just unfortunate nature of what I would like to. I cannot do, but I can get a series hybrid plug-in a vehicle which will do all I want to do. So hopefully that answers your question, and thank you for asking me that personal question. I think we probably not have any more questions at the one.
Thank you indeed, Ricardo. That was really great, and thank you to everybody who joined us today and who submitted questions. I think we could probably go on all day here, but it was really good. So thank you for that. This was the last in our current series of lunchtime webinars. We go by term time, so we will be back with more lunchtime seminars in the autumn. And of course, we'll have other events over the course of the summer, so do please keep an eye on the website for those, and if you haven't already done so, you can subscribe to our mailing list. And if you missed any of our previous webinars, you can find them all on YouTube. So that's it for today. Thank you very much again for joining us, and have a great afternoon. Bye-bye.